So our first invited speaker is Chris Martens. Dr. Chris Martens is an associate professor at Northeastern University, a computer scientist and a computational media scholar in the field of digital games and narrative. Chris brings a transdisciplinary perspective to computational media, informed by a strong foundation in programming language theory, leading to new insights about how logic programming, modal and linear logics, and type systems can model key properties of virtual worlds and virtual agent reasoning systems. Chris currently directs the Principles of Expressive Machines Laboratory, POEM for short, in research on digital games and interactive narrative. Their work has been supported by the National Science Foundation, the Laboratory for Analytic Sciences, and the Air Force Office of Scientific Research, including a prestigious NSF Career Award. Thank you, Chris, for accepting our invitation, and we hand it over to you.
Thank you so much for the intro. Let me make sure my screen share is working. All right, great. Yeah, thank you again. I'm really excited. This is actually my first participation in PADL ever. I really obviously appreciate the scope of what this conference has been doing for the last many years, and I wish I could be there in person. I am at Northeastern now, so I'm local, and I was planning to be there in person. But I tested positive for COVID a while back and still am. So this is what we have. So I wish I could talk with all of you. Maybe I'll hang around on the air meet if folks are around for that. I really do, value the face-to-face conversations here. So I'm hoping for some interaction, not just me delivering this talk. You're welcome to, ask questions at any time. Yeah, I want to get to know folks and chat with you. But thank you so much for inviting me. I'm really excited to present some of my work on what I'm kind of tongue-in-cheek calling declarative content generation as a contrast to what you might have heard of called procedural content generation, and in the context of creativity support tools. You can access these slides at the URL shown on the slide, and hopefully that URL will show up throughout the talk if you miss it. All right, so yeah, you can check out my new website in progress at convivial.tools. If you get that reference, I want to be your friend. I am, as I was introduced, an associate professor. I have a cross appointment between computer science and art and design at Northeastern, which is awesome. I love being able to have colleagues across those areas. My pronouns are they, them. My research focuses generally on the procedural systems that underlie games and stories, and on building and evaluating tools and languages for designing those things, especially when they involve complex or emergent systems and some kind of human creativity. My bread and butter, academically speaking, is functional and logic programming, which I still love and try to use as much as possible. But I also really, really like how weird humans are and how tricky it can be to make things that that humans find easy to use and to think about and to reason about. So that's something that's newer to my practice as an academic, is incorporating like cognitive science and human subject studies into what I've been doing. But I really like it. I think it's really valuable to think about these things from those two perspectives. So yeah, so procedural content generation, generally speaking, is a practice that the term at least arises from digital game design, and from some of the earliest digital games. In fact, you may recognize the 1970 game Rogue, or I don't know if that's Rogue or NetHack. That might be NetHack in the corner there, as well as one of the early graphical games, Elite. So these, and then of course many more modern examples, including Spelunky, Civilization, and so on. No Man's Sky is on there, I think, and a couple of more indie titles. But so the idea here with procedural generation is that rather than hand authoring all of the content for your game, usually in reference to the game environment, the physical space that the player is navigating, whether that's a 2D level map or a 3D terrain, or a galactic universe with planets that you can land on and so forth. All of that stuff, rather than hand authoring all of its detail, you write an algorithm to do it. And this means that this took off in the first place because computers had low enough memory constraints that you actually needed to do that in order to avoid having to hold all of your world data in memory. So like Elite, I think, originally did this to basically to save memory footprint, to substitute space usage with time usage with computation. But it's also used and has been used for a long time to support infinite replayability. I'll get into a little bit more of that, those details in a moment. But I also want to draw your attention. My slides are taking a while to load. That's a bit odd. I also want to draw your attention to kind of another origin of a lot of the same ideas, but that doesn't necessarily come from people in games. In fact, a lot of people, a lot of these ideas have come from sort of pre-digital computers and art movements that involve manually executed rules and procedures. And this is generative art. And, I include under that umbrella parametric design. So this is the idea that you're creating some kind of artifact, whether it's a two-dimensional image, three-dimensional model, or even something in physical space, such as textiles or furniture or architecture that might exist in the real world. But you're generating those things through by specifying some constraints and leaving important creative decisions up to either randomness or some other algorithm that's going to satisfy those constraints to create objects that you might not have necessarily thought of creating by hand. Recently, I've been participating in this really cool online activity called January. It's been happening for the last few years in the month of January, where every day there's a different prompt to do some kind of generative art. And you can take a look at some of the work that I've been doing for this at the link on the slide. And some of it's displayed on the slide. And you can also see like a sample of some of the prompts that are given. So these are basically just little creative coding exercises. You can kind of think of it as a way of like filling up a daily sketchbook with different prompts, but your sketches are made out of code rather than drawn on paper. Most of the time, actually. I did this Voronoi tessellation. I did a version of that by hand recently, which was really fun. But yeah, so you can see there's prompts like making a perfect loop, making something in 10 minutes, glitch art, intersections, and this is just a sample, of course. This one was a response to the prompt of asemic writing, which is like symbols that kind of look like writing, even though they don't come from an established alphabet. This was like, use a color palette from an album you like. This one I think was inspired by plants, and it's a cellular automaton, loosely inspired by how moss grows. This is a Truchet tessellation, which is just like any arbitrary of the four orientations of a square with this diagonal pattern, randomly chosen to generate these kind of maze-like patterns and so on. Oh, this one is a Soluit drawing, which, speaking of generative art traditions that come from before or that don't depend on digital computers. Sol LeWitt is an artist who basically says, my job as an artist is not to actually paint the thing on the surface. My job is to give a sequence of instructions that anyone can follow, and then they can render my work anywhere they want, right? So this is one of his famous wall drawings, in which the instructions were something like, this is actually one panel of 7, right, where the first 3 panels are just the instructions for drawing the yellow, blue, and red lines individually, and then you get every combination of them on the other panels. Yeah, anyway, really cool ideas in the January prompt set that I encourage you to check out if you want to get a sense for what generative art is all about. So I talked a little bit about why we do this. So just to reiterate, originally it was about kind of reducing the memory footprint, and the notion of replayability still persists, as well as this concept of well, if I have an algorithm to choose, to recombine elements from an infinite set, or to make infinite decisions, an unbounded sequence of decisions about how to construct an artifact, then my player never has to stop playing my game. We can infinitely generate. We can, as soon as they get to the boundary of the world, we can just generate more of the world. Exploration never has to stop, right? We can potentially save some manual authoring. Is kind of a motivation, but in practice, I think you'll find a lot of game developers will say manual effort is not actually that, when you write a procedural generation system, you often spend more time authoring that than you would have just authoring comparable amounts of content in the beginning, because you're sacrificing some amount of control over the quality of what's being generated, and in order to get that really right, it takes quite a lot of work. But the motivation that I'm kind of most interested in my work recently is generative algorithms' ability to augment human creativity by enabling new ways of exploring the design space. So what do I mean by that? So by navigating the design space, what I mean is that latent in all of these algorithms, and particularly obvious in things like parametric design, is this concept that you have some amorphous idea of the artifact that you're trying to create, even outside of the space of generative algorithms, right? You sit down, if you're an artist and you sit down with a blank piece of paper, there's infinitely many things, even with a fixed set of materials, right? There's infinitely many things you could create with that. And so there's a huge possibility space. And part of what you're doing is kind of trying to whittle down that possibility space by introducing constraints, but also sometimes to expand it by introducing some new element, or to get yourself to explore a piece of that design space that you might not have thought to explore. Sometimes that can come from adding a rule, you have to only draw straight lines, for instance. Sometimes that can come from, in the case of this curve-aligned bench image that I like so much, it can come from saying I'm going to give you some specifications that have a range of values that they can take. This bench, probably has to have a flat surface on the bottom to sit on the ground. It has to have some kind of relatively flat surface on which people can sit, and some kind of back. But the particular shape and all of the, and maybe it has to follow some kind of smooth curve, right? But the particular specifics of those curves, I leave up to the algorithm to make those decisions. So there's many possible benches that this could produce, but you're kind of saying there are some decisions that I don't know how to make creatively right now, and I want to cede control over those creative decisions to an algorithm, just to kind of see what is possible that maybe if I were making those decisions manually, I would not have discovered. And my colleague Mike Cook this URL is annoyingly overlapping the text, but nonetheless, this comes from a little article that Mike Cook wrote about the concept of possibility space and generative space, where he uses a Minecraft world generation algorithm as an example, and kind of says, well, you know, there's infinitely many possible Minecraft worlds we could generate, including the one that's just completely flat grass, which is boring, and like maybe we don't want that to be included in our generative space. And so the art of creating a generative algorithm is basically to draw this green circle, right? To figure out what is the subset of possibilities that makes sense for me. And you're not going to know that in advance, right? It's going to take some kind of collaboration with the algorithm. And that circle will get bigger and smaller kind of as you iterate, as you figure out like what the actual specifications are for the type of things you're trying to generate. Okay, so for the rest of this talk, I want to talk about just like to narrow our focus a little bit, a specific example program that we can kind of zoom in on, look at up close, and two different, like a sort of standard imperative approach and declarative approach using answer set programming. I'm going to get a little bit into more detail about answer set programming in particular, since that's my declarative language of choice recently for procedural generation. And then I want to shift focus over to some discussion, which is mostly just me like philosophizing a little bit and asking questions which very well may have answers that come from this community, and I may not know them. So it's going to be sort of an invitation to bring the rest of you into this conversation and kind of see what might be possible in the space. Okay. Yeah, something has gone wrong with my formatting. I'm sorry about that. But in any case, the motivating problem that I want to zoom in on is procedural terrain generation. In particular, imagine you have a 2D square tile grid that's a representation of the map of a world, and it's basically a height map. So this represents terrain in the sense that each square grid has a certain height, and maybe everything below a particular height is water. So you come up with sort of these continent shapes. This is a common, some variation on this is a common thing to do in a lot of procedural world generation. So yeah, so when we discretize this to grid cells, it's fairly easy to specify what our desirable properties of terrain are. So if we want to say at least like we have some kind of relatively smooth change in elevation everywhere, then we can say no grid cell has a neighbor whose height differs from it by more than some maximum number. I've usually just used 1 in my examples. So just to kind of give away at least the high level, like, so if I were to run each of the programs that I've implemented to satisfy this constraint, I did one in something called p5.js, which is, if you've heard of processing, it's that for the web. If you haven't heard of processing, basically the idea is it's a bunch of libraries for drawing and animating embedded in a standard programming language. So for processing, that was Java. P5 is a JavaScript version of it. And you can actually go to like the URL. I can actually, don't think if I open a tab, you'll be able to see it. But if you go to p5js.org, you'll be able to learn about that whole project, which I think is really cool because they're kind of setting up a framework for artists to learn programming if they don't know how yet, and basically for anyone with an interest in creative coding to learn more about it in a way that has a lot of like examples and really accessible tutorials and that kind of thing. And then the second one here is generated by an answer set program. So seeing if my animations work okay. Yeah, they're a little slow, but they're going. Okay, so in the P5 program, my approach was to implement a cellular automaton. So you might say, actually, this is a CA program, and maybe the host language doesn't matter. Maybe it does. But so basically it's a cellular automaton where the grid cells follow the rule. If I have at least some number of neighbors that are too low, then give them my height. Like give one of them my height at random to a random low neighbor. What you get as a result depends a lot on how you initialize the grid. So if you this is my initialized sparse version at the top that starts with basically randomized heights, but with a bias towards lower ones. And this is one where I have higher, like a bias towards higher heights in the center. And I like the lower one better, right? Because it creates sort of like an island or a continent concentrated in the middle most of the time. But yeah, so obviously what you get as a result depends a lot on that. The answer set program, by contrast, is given a rule that no cell, basically just the specification I gave on the original slide for how I define the problem, right? No cell may be more than max height from its neighbor. There's another constraint that I add in order to keep it from just giving me the degenerate oops all ocean solution, which is if you've ever used answer set programming, it's very common for you to like very carefully articulate all your constraints and then for it to just be like, okay, I followed your what you said, and now I've given you completely boring solutions to that. So you have to put in some other constraints to give you interesting things, and I'll get into that in a bit. But before I do that, I want to give a brief primer on answer set programming, just in case folks are not familiar with it already. And so this is kind of the part of the talk that I'm calling declarative content generation. So answer set programming is a style of logic programming where instead of running queries, like you have your facts and rules as usual, but instead of running queries to get like a set of answers for one particular query, a set of like unifications for the variables, you instead get what's called a set of stable models. So you don't need to look at this code too closely. I'm going to explain it bit by bit. But roughly speaking, like your input is a logic program, and then your output is a set, or sequence, I guess, of answers, which themselves are sets of ground predicates. So like if you're generating, this is a slightly modified, I apologize for mixing examples, a slightly modified terrain generation algorithm where you have different terrain types, and you can kind of say at each tile you can have any of the following types of terrain, and then your answers are basically all of the many combinations of assignments from tiles to terrain types. So to kind of build this example from the ground up, the way that stable models work is basically you give a sequence of facts, and then a stable model is a maximal solution or a maximal like saturation of that program that is consistent with those facts. So if you say one of my facts is ocean, one of my facts is forest, then you'll have exactly one answer, which is both ocean and forest have to be true. ASP, the way it sort of differs from ordinary logic programming, one of the key ways it differs is through this concept of a choice rule, which is sort of a disjunction, right? I see this as kind of saying whatever is inside the bracket, if you have like brackets A, it's kind of like saying A or not A. And if you're a constructive logician like me, then you'll see why that's different from, why that's meaningful at all, right? But if you're not, then it can be a little counterintuitive, right? So what you're saying is, I'm not establishing by fiat that ocean is a fact that has to be included in this world. I'm giving you the choice of whether to include it or not. And so there are many, so there are valid answers that can make the choice to include it or not to include it, as long as they don't violate any of the other constraints. So in this little tiny program, I don't have any other constraints. I'm just saying you can include ocean or not, and you can include forest or not. And this results in, instead of in just a single answer, it has 4 different answers, all possible combinations, either, none of them, just ocean, just forest, or ocean and forest together. All right, so now, like with that intuition in mind, if I say that ocean is a possibility, and then ocean implies forest, then how many answers do we expect? If you're online, you can type your guess in chat. Or I don't know if I can hear people in the room, but if people in the room want to guess, you're welcome to. I know I didn't set up the expectation that I would be requiring interaction. Okay, sorry, what was that?
People guessed 2.
2. All right, yes. Good. Right, you're getting the idea. So you can either not have ocean, in which case the empty world is the answer, or you can have both ocean and forest. Okay. You can, so another key concept in answer set programming, okay, we've got choice rules. The next thing is integrity constraints. And integrity constraints are this idea of you can have a headless rule. So you can have a : our good friend here, but without anything at the head. And what that means, again, might look a little familiar if you know about like sort of how negation is defined in constructive logic. What you're saying is everything to the right of this implies false or implies the model is not consistent. So it's a little bit like not, but it's a strong negation. If that means anything to you, if not, just think of it as negation for now. So what this program says is wet or not wet, dry or not dry, but don't make it the case that both wet and dry. And so you're saying this is kind of a mutual exclusion, right? You can have either one, but they're mutually exclusive. So this one has 3 answers, either neither wet nor dry, or just wet, or just dry. If we augment that program with the implication that wet implies ocean and dry implies forest, then we still have 3 answers, but the wet world has ocean and the dry world has forest. And now we can start, now we can get away from propositional land and start actually defining predicates. And using logic variables. So this adds a little bit more notation. All of it is syntactic sugar, kind of. And I can get into more about what this means if people have questions. But at a high level, this is basically saying the number on the left is a minimum and the number on the right is a maximum. So I'm constraining there to be exactly one of these tile facts. So the tile at area will be capital T tile for some tile that is one of our terrain types for each area. So so you can kind of read everything to the right of this as a for all, and this like colon syntax inside the choice rule as like an exists or a constraint on the variable inside. So what I'm doing here is I'm assigning exactly one tile type to each area. And I'm saying, and then I'm giving it an integrity constraint that says mountains and ocean can't be neighbors. So if area 1 has type, if the tile at area 1 is mountain, if the tile at area 2 is ocean, then and neighbor area 1, area 2, then false or disallowed, right? Then these 3 things taken together are not allowed in my models. You can also add hard-coded parts of the map. So if you want to say, oh, my top row of my map has to be entirely ocean, then you can say, well, any value n in my y range, left-hand column, I guess this would be. Right, so any valid n in my y range, the cell at 0n is going to be ocean. So you can kind of like hand impose specific like parts of the map that have to be locked into specific values. Okay, and then the answers you get if you run, so I'm using Clinko as my tool for answer set solving, and the answers you get correspond to possible generated maps. The answer set, that is the complete set of answers you would get, is like corresponds to this possibility space or this generative space that you're honing over time. So I mentioned I use Potasco Clinko as my tool set. There's also a cool way to integrate ASP with Unity that you can check out by my colleague Ian Horswell. And yeah, people have done all kinds of really cool stuff with this. The basic workflow is one that corresponds sort of to Amina Torlak's notion of solver-aided programming. So I kind of think of it as solver-aided content generation. You develop an ASP program that is kind of your initial specification of what your generative space wants to be. You throw it to your solver, generate a bunch of examples, and then as a human, you're going to inspect those examples, evaluate them, see if they're kind of meeting your standards of what the generative space ought to be, and then you'll refine them. So the process of building an ASP program to generate things like terrain maps is very, very iterative. Usually start with a small program with a small number of constraints, get a bunch of examples that you're like, oh, I didn't want that one in there, and then you add kind of layer more constraints as you go until you get a generative space that you're more or less satisfied with. One of the cool things is that since we're specifying everything in terms of, relationally rather than, imperatively, we're not just writing one algorithm whose input is constraints and whose output is examples. We actually get kind of a bidirectional thing here, which I've used in some of my research. And I think of this as sort of operationalizing the duality between synthesis and analysis. So this workflow that I just described of writing your constraints and then getting examples is the synthesis approach. But you can also think of this as, you can also run that same program in sort of a different mode as an analysis program where you put in specific examples and maybe some queries about their properties, and then that very same ASP program can tell you the answers to those queries. No, you don't have queries like you would in Prolog, but there are ways of kind of specifying your queries as input to your as additional constraints in your answer set program, and then inspecting the answers you get out and interpreting those as answers to your queries. So some cool things you can do with this. I've used ASP in a project with a bunch of teammates at UC Santa Cruz to generate game rules and to do sort of deep readings of the meanings of those game rules via ASP. And we call this system Gemini, and it takes advantage of that sort of bidirectionality of doing both synthesis and analysis. I also have an ongoing project, which if you were at ProLala yesterday, you might have seen a little bit about, which is this concept of generating explorable narrative spaces. So implementing something called a narrative planner, where you can put in initial situations for a story, and then it will generate all of the possible stories that might emerge as a result. There's some links to papers here. Again, sorry, they're covered up. There's also a tile map generator project that came out of a couple of students in one of my classes implementing an ASP thing to do like tile maps for tabletop role-playing games. I'm interested in kind of usability efforts around this, and I'll touch on some more of the ideas here at the end, but one of the things that I really liked about this tile map project, this is a screenshot of what my students came up with, was this idea of kind of having a structure editor for ASP rules. So a lot of people complain that ASP syntax is completely inscrutable, and it's really, really hard to write correct ASP programs. So one of the ways that we can mitigate that a bit is by giving people a way to write ASP rules that are always syntactically valid, where they don't have to think so much about am I getting the syntax right? And so one just like known way to do that from computer science education is this concept of a structure editor. You only allow people to construct syntactically valid expressions. And in this case, you can even kind of get domain specific about it because you're talking about square grids. So they provided this little sub-language of rules that you might want to impose over your square grid map. Like there's at least a certain number of houses, at most at least exactly. This is not a good representation of all the types of rules they allowed, but some of the rules are about like the distance between certain objects or what certain objects can be adjacent to others, and so on. So you can kind of, specify what you want in terms that are legible as having to do with tile maps rather than sort of this arbitrary logic syntax. Okay, I'm going to take a sip of water. So back to this terrain generation program. You now, at least if you remember the things that I said about choice rules and integrity constraints, you now have the knowledge to understand this program. So let me go through it briefly. So we are going to say our max height is 8. So we have a range of possible heights from 0 to 8. This choice rule selects a height for each cell from among the possible heights. And then this neighbor height rule is is actually defining what it means for a neighbor, for two heights to be in the neighbor height relation, right? Which is to say, height 1 and height 2 are going to be at most 1 different from each other. So h1 and h2 with possible heights. h1 minus h2 is less than or equal to 1, and h2 minus h1 is less than or equal to 1. And then finally, we have our integrity constraint, which says if my height at 2 neighboring cells is h1 and h2, and they're not in the neighbor height, those heights are not in the neighbor height relation, then rule out that model. So what that should leave us with is only those models that for which every cell obeys the neighbor height relation. Pausing here for questions.
For you, Chris.
Yes. Yes, please. I can't hear anybody.
Hi. What happens if you take the negated neighbor height and make it the conclusion of that rule instead of making it an integrity constraint?
You take the negated neighbor height and you make it the, okay, so if you say basically height x1, y1, h1, height x2, y2, h2, and their neighbors implies not neighbor height?
Implies neighbor height.
Implies neighbor height. Ah, okay. So what happens if you do that? The meaning of adding a rule or effect, but including rules, is basically that you're providing a new way to construct a neighbor fact if you do that, right? So you're saying, here's another way you can prove neighbor to be true.
Okay.
Yeah. So that would not do what we want.
Right. Okay.
Yeah, that's a really good question though, because that gets at sort of why these programs are a bit counterintuitive, because we're really distinguishing between this like I am giving ways for things to be proven versus I'm providing new ways for things to be proven versus I am like enforcing this as a constraint, which must hold, otherwise the world is invalid. Great question.
Hello, I have a slightly different question.
Please, yes.
So in the neighbor height relation, there's some arithmetic. What do you do in ASP to ensure that the models are still like sort of finite? Is there?
Yeah. Okay. Yeah. So there's arithmetic here. The models are finite because because the programs are actually finite. So you'll note that I had to specify as like in a ground way what all of the possible heights are. They range from 0 to max height, and Clinko, I think by default, and most answer set solvers will actually completely ground the program before they start solving it. So there's not it's a very unusual way to do logic programming, because you're not doing like unification on the fly. You're not assuming your domains are infinite. You're enumerating all their possibilities and and then solving from there. So because the set of possible heights is finite, the set of the these computations, like subtraction is a function. I'm not actually sure. I think in like the Clinko tool set, they probably have, some like implementations of various arithmetic operators, and they make assumptions about the properties of those arithmetic operations, like that subtraction is a function, for example, that will make sure that those, like this is a total operation you can do for any two values, and the sets of those values are finite. But yeah, also a good question. Thanks. Okay. All right. So then the way that we remove the degenerate example of like oops all ocean or any other tile type is we can add some additional integrity constraints. So we can compute the minimum and maximum height globally in the graph, and then we can rule out models in which the max minus the min is less than some global min difference. And here I've set it to 3. So basically this is saying we have to have a range of heights that's at least 3 different from each other. So if we add in that constraint, then that will get us the map that you saw in the previous slide. So at this point, I want to get into a little bit of discussion, and I'll ask you, the audience, maybe I should have included the images again. If you want me to go back to that slide, let me know. But consider the P5JS Cellular Automata and the ASP program. What sorts of things do you notice when you compare them?
Could you please go back to the slide?
Yes. I may need to, this might break. Okay, am I still sharing?
Yes.
Good. Okay, let me go back here.
Thank you.
Okay, so notably, I'm only showing you one example, which is should always be suspicious when someone says they created a generative algorithm and then they only show you one example of what it created. But these are, so the one on the left is an example from the Cellular Automata program with the center bias, initial constraints, and the one on the right comes from the ASP program. Is there other information it would be useful for me to show? Like this was the animation of the Cellular Automata. My CA rule, maybe I can fix the formatting while I'm at it. I really don't understand why it got messed up.
I have something that I noticed in the ASP picture. The water doesn't seem very real.
Yeah. Okay. So in the ASP picture, the water doesn't look as maybe ocean-like as we would like.
Too much variability, or
Yeah. Versus in the CA program, it kind of has like bigger sections of consistent depth, which seems more appropriate. Yeah, I like that observation because it kind of forces us to think about, well, what is it that makes the ocean, what do we think oceans look like? Like what are oceans in the real world actually like, and how does that show up on a map? And how could we translate that into some kind of programmatic constraint? Because yeah, the Cellular Automata program kind of just does that naturally, but the ASP program, we would have to like specify that property as a constraint somehow to get it to do that. In chat, I see the P5JS one is smoother. The ASP seems to have some sort of square-like artifacts. Yeah, both in the ocean sections and in the landmass sections.
There's one more.
Yes, go ahead.
The Cellular Automata one seems to have this nice separation between like the rules and the seed. So the initial state matters and you can tune it by tweaking the initial state. Whereas with ASP, it's just like whatever the solver spits out.
Yeah, definitely. Right. Yeah. So you can kind of maybe reason more about the relationship between the initial state, like the seed, as you were saying, the initial state, and how the rules will change that. Whereas you can't do that in the ASP program, which I think is pretty related to another observation I have. So if I go back to this slide, and let me get back into presenter view as well.
Hello. I have a question.
Yes.
Could you simulate cellular automata with ASP program with some kind of layers or so?
That's a great question. Yes, you could. Keep that in mind, and actually the rest of the audience, like, think about that question as well as we go through some of the next questions. I actually hadn't considered that as an approach. I think that's going to be interesting to talk about, but let's get into some of the other questions about just thinking about these two programs separately first. But yeah, thank you for that, like, seed of thought. I think that will be relevant. So what I notice about the difference between these two programs, first of all, they both have things that we're calling rules, but they play totally different roles, right? In ASP, the rules are sort of global constraints, and in the cellular automaton, a rule is about sort of an imperative, like at each step, this, like, a cell will do this under these conditions. Someone already pointed out that the initial state has a huge impact on what we see in the cellular automaton, but similarly, or I think, like, not necessarily exactly analogously, but we also like, we can't just talk about this key property of the like smoothness for the maps. We also have to give some additional things, and in ASP that turns into like these additional constraints to rule out degenerative cases. The second to last bullet point here is about this kind of like, and this is what I was saying, kind of maybe relates to this idea that you can think about how the initial map relates to the rules in the CA. One thing you'll notice is that I was able to give you animations for the CA version that show you the each iteration as the rules take effect on the grid. And I only gave you still images for ASP because we only have access to the output. And I think something you'll find is that generative artists really, really like to watch algorithms run. They like to be able to observe those intermediate steps. I certainly do. I think it helps a lot with intuition about what's happening, and you can, it gives you a natural hook into, instead of just running each frame, like saying, inserting a human in the loop interaction, you can say only do this on a mouse press, and then you can click through each step individually and inspect them much more slowly. So that's something I think is really compelling about the CA version that I don't really see how to achieve with an ASP program. On the other hand, the whole possibility space in the CA version is completely latent because it's using just like math.random to make choices, and so there's all these sort of decision points which are just a result of having some randomness in the program, but that are not like explicitly enumerated, and so you can't get a sense for like, well, okay, what are all the possible outcomes given a certain input, or what is the probability distribution? And ASP, one of the cool things about it is that it like makes very explicit, like, this is the total possibility space. It is in fact like the thing you are representing with your program. And that becomes really important for going back to this diagram of like understanding possibility spaces, helping users understand the generative space. One of the most interesting lines of research, I think, in this area right now is tools that help people understand the generative space. There's something called expressive range analysis, originally introduced by Gillian Smith in 2010, which is all about being able to kind of visualize, usually as some kind of heat map, all of the possible results, or just a sample of the results as you run your generator like thousands of times, to get a sense for what their properties are. And you have to specify what properties you care about. And usually they're things that are numerically ordered in some kind of total order, so you can graph them along an X and a Y axis and see how things cluster together and so on. But if your things are like two-dimensional visual objects, that can be fairly natural. And in 2016, Mike Cook introduced this tool called Danesh, which I'm showing an animation of on the screen, which both kind of shows you like the chorus line of a sampling of possible outcomes for your generator, as well as this expressive range analysis heat map, and lets you kind of inspect different options from among those that are possible to generate. And this kind of tool, like this is all like very, I don't like outside of the norm of what people tend to do in procedural generation, as far as I'm aware. I mean, game developers use a lot of proprietary tools they don't tell us about, but as far as I know, like most people are just kind of generating things and like doing generate and test, basically this process of generate a bunch of stuff, look at it, make, kind of eyeball it, see, is that about right? No, I'll tweak something, or yes, okay, ship it. Right. And this like is a way of giving you, if not exhaustive, at least a little bit more systematic analysis of your generative space. And although the generative space is never explicitly represented in the Cellular Automata program, a tool like Danesh could work for it, because you can run a bunch of samples and sort of do this as dynamic analysis. In ASP, like you have a static definition of the possibility space, but in some ways that actually makes it a little bit more challenging, because sampling the answer space, like unless you have a small enough answer set that you could actually inspect, like if there's finitely many answers, you can inspect them all. If you just want to take a representative sample, that's pretty challenging. Like it has a way to do sort of random exploration of the search space, but it doesn't work very well in my experience. And if you take if you say like, give me 10 answers, and it spits a bunch out, they will often differ by like one decision, and otherwise be exactly the same, even if you have random mode on, which is weird and confusing, and makes it really hard to kind of get a sense of what the generative space actually is. The order that it produces answers, even without random turned on, is difficult to reason about. I've also had some similar experiences and some conversations with people around mini-Canron, and how that's also a challenge of like figuring out, well, could I get these answers in a different order, or could I, only sample, like, could I sample every nth answer like that from the possibilities space? So yeah, so thinking about this concept of like, particularly of like embedding the CA program in ASP, that might be a good answer to some of these questions. So I feel like it would be really interesting to try to relate these two programs. I said that these programs are both satisfying the same kind of specification, but do they have the same generative space? They probably don't. If they did, how would we prove it? And like, what does same even mean? Do we need them to have the exact same probability distribution over those answers, or could it, or like the ASP program like sort of represents a probability distribution? Is it possible to show the CA program actually adheres to it based on how random choices are made? Or maybe even just at a simpler level, could we show that like the possibility spaces are the same? And then going back to this concept of like inspecting intermediate states, could we do something similar with an ASP program? Well, what does an intermediate state of a solver look like typically? And is that actually meaningful or useful? Like, would we get, would it be interesting to see like the way that the possibility space might shrink as like more constraints are applied? That's not even really how ASP solvers work, as I understand. So I don't even know what that would look like. I think it would be interesting to understand it. Maybe there's already work happening about this and I don't know about it, and I'd love to hear from you. Yeah, if there's already research on inspecting or stepping execution of declarative programs like answer set programs, I'd like to know. And okay, there's a little more philosophy here at the end, but I'm going to skip that because we're at 10 o'clock. And basically just conclude with the overarching point that I think PCG is a rich application area. I think more people interested in declarative programming and people designing languages should look at it and think about whether something you're doing might be relevant. And if you're interested in the space generally, I can recommend some follow-up resources. So there's an online book written by many of my academic colleagues called the PCG book. There's also this textbook called this, we can get in paperback or hardcover or Kindle, called Procedural Generation Game Design, which has a lot more industry perspective than the PCG book. I think it makes a really nice complement to it. If you're interested in ASP for PCG specifically, so Adam Smith at UC Santa Cruz was kind of the first person to publish on that particular application. So check out his website and papers. And then in general, I also really like Amit Patel's website for game AI stuff in general, which includes a lot of procedural generation. And Amit Patel is like a functional programmer at heart. So everything he explained, like all of his explanations, first of all, they're just like beautiful in general, but they're also like they're good. They're easy to follow along with if you have kind of a declarative intuition about things. That's it for me. Please get in touch. I am happy to take questions if we've got time. Otherwise, hope to see you around. Thanks.
Thank you, Chris. Maybe we'll take one question and then the questions from the, yes.
Thank you, Chris. I was wondering how you would compare answer set programming, since you were talking about probability distributions, to things like stochastic logic programs or probabilistic logic programming, and what the trade-offs might be.
Cool. Yeah, I've been thinking about that area recently, kind of for the first time. I had previously kind of shied away from probabilistic and stochastic programs because of, I don't know, mostly just a bias, like feeling like, oh, it's too tricky to think about. Like, I'm not good at reasoning about probability. I mean, nobody really is, but like thinking like, I don't really want to like explicitly define my probability space. I just want to I just want it to be latent in what I describe. But recently I had a student in my class on PL for virtual worlds last semester, who's doing research on probabilistic logic programming, specifically Problog, get really interested in the space and start chatting with me about kind of comparing Problog and ASP. I think there's some real promise there. I do think I think that can help a lot with this concept, specifically of like expressive range analysis and being able to like do any kind of reflection over or meta-analysis of the possibility space and how things change when you modify probabilities. I think there's some really useful things there. I think the tooling for things like Problog, in my experience so far, is not up to where like Clinko is for this particular application. It can be tricky to encode certain types of constraints that are common. So I think there's some like usability and like, I don't know, some language design issues, but I don't think they're insurmountable. And I think that's a really promising line of work. Does that answer the question?
It does. Thank you.
Awesome. Thanks.
Well, thank you very much, Chris. Let's thank Chris.